Okay, thank you. It's a pleasure to be here. Thank you for the invitation. So I'm going to talk about modular forms on exceptional groups. So the modular forms in the title does not mean automorphic forms. It means a very special type of automorphic forms, which I'm going to describe. Okay, so first, classical modular forms. What do I mean by that? So take a reductive group G over Q and take a maximal compact subgroup K of the real points. And then suppose the group G is of the form is such that the symmetric space G of R mod K has a Hermitian tube structure. So in this case, there's a very special class of automorphic functions, the modular forms. So these are the automorphic functions that give rise to holomorphic, the automorphic forms that give rise to holomorphic functions on the symmetric space. So those automorphic forms have a very robust Fourier expansion. And so the point of this talk is that for certain exceptional groups that don't have Hermitian structure, they are still a good notion of modular forms. Okay, so again with the classical modular forms. So for example, take the group GSP2n. So the group fixing the subgroup of GL2n that fixes a symplectic form up to similitude. Then the Siegel upper half space, this space Hn, that's a complex manifold that consists of the x plus I y, where x and y are symmetric n by n matrices, and y is positive definite. So that's the symmetric space for sp2n. And so of course it's a complex manifold. So GSP2n acts on two copies of this symmetric space, the upper and lower Siegel half space via this action at the bottom. G times Z is AZ plus B over, or times CZ plus D inverse, where G is ABCD in n by n block form. So this is, of course, a group that has, whose symmetric space has Hermitian structure. Okay. And the classical Siegel modular forms are holomorphic functions that satisfy this functional equation. F of AZ plus B times CZ plus D inverse is determinant CZ plus D to the K times F of Z for all ABCD in some congruent subgroup of SP2N. And so because they're holomorphic functions, they have a really nice Fourier expansion. So namely, if F of Z is your Siegel modular form, then it has a Fourier expansion summing over n by n symmetric matrices that are positive definite with rational coefficients, e to the 2 pi I trace tz times a of t. Okay. Okay, and of course, almost all of these a of t's are 0 except for t and some lattice there. Okay, so equivalently, if you write this in terms of the automorphic function phi sub f associated to f, that means that when you restrict this automorphic function to the Siegel parabolic, so inside of GSP2nr, then you can write the Fourier expansion in terms of the unipotent radical of the Siegel parabolic and the levy of the Siegel parabolic. Okay? Okay. So what is this talk not about? So if you take E6 and E7, then there are two real forms of them for which the symmetric space is a complex manifold. And in particular, if you take the group E7, it has a form of it that's rank 3 over the real numbers, and that group has a Hermitian tube structure. The symmetric space does. And so you can consider modular forms, holomorphic modular forms for that group. So this talk is not about those, but I'm going to mention a little bit about them anyway because they'll show up later. So what is the symmetric space for this group E7 that has rank 3 over the real numbers look like? So if you take the octonions with a positive definite norm, so that's an 8-dimensional real composition algebra or whatever, and then you can form this 27-dimensional space J, which is the Hermitian 3x3 matrices over the octonions. So that's called the exceptional Jordan algebra. And then if you take and then this group E7 that has rank 3 over the real numbers, it has a symmetric space that looks just like the Siegel space that I just mentioned for GSP2n. So now the elements are x plus iy, where x and y are in this 27-dimensional Jordan algebra, and y is positive definite. And you could talk about modular forms for this group. So automorphic functions that give rise to automorphic forms that give rise to holomorphic functions on the space Hj, and then they have some very explicit and simple Fourier expansion. Okay, so one important example of such a modular form is Kim's modular form on this group. So that's a holomorphic modular form that generates the automorphic minimal representation. And so anyway, just to reiterate, so this talk is not about holomorphic modular forms on E7, but they will show up later. Okay, so what's that? There's also, you mean the Hermitian structure? Yeah. So E6 also has a real form for which the symmetric space has Hermitian structure, yeah. Sorry, what did you say? That the symmetric space has Hermitian structure? Yeah, of course. So in E6, it doesn't have a tube structure, but anyway. So the talk is not about that. So what is it actually about? So if you take, say, the Dynkin types G2, F4, and E8, so no real form of them has a symmetric space with a complex, which is a complex manifold. So you could ask, are there very nice automorphic functions on this group? So functions that give rise to automorphic forms that give rise to very nice functions on the symmetric space. So it turns out that there is. So there is a notion of modular forms for those groups. And it was initiated by Gross and Pollack and Gangros and Savin. And so the groups that I'm going to be talking about are the split forms of G2 and F4 and forms of E6, E7, and E8 that have rank 4 over the real numbers. So to reiterate, so this, for example, this E7 here that we'll talk about has rank 4 over the real numbers, whereas the one that has Hermitian structure has rank 3 over the real numbers. Okay. So the main theorem, sort of where we're going, is that the modular forms on those groups do have very nice Fourier expansions, sort of as similar as possible to the holomorphic modular forms on groups that have holomorphic structure. And it's a very robust Fourier expansion. And so examples of these modular forms include the automorphic minimal representation on E8, on the form of E8 that has rank 4 over the real numbers. Another result that I'll mention later is a modular form on G2 for which all the Fourier coefficients are integers. So the fact that this theorem that I'll be discussing a lot says that these Fourier expansions are sufficiently robust that you can sort of normalize them integrally, and so it makes sense to talk about integral Fourier coefficients. Another example of one of these modular forms will be an Eisenstein series, or Eisenstein series. So for example, if you take a holomorphic cusp form on E7 3, so the form of E7 that has a Hermitian symmetric space, then you can make an Eisenstein series on E8 using that inducing data, and at a very special point, you'll get one of these modular forms on E8. And then I'll also mention some modular forms on E6 and E7 that have very nice Fourier expansions. Okay, so I wrote here that they have distinguished and singular Fourier expansions. So those are precise terms that I'll get to later that mean that many Fourier coefficients are 0. Okay, so what's the underlying representation theory? Like I mentioned, the exceptional groups, G2, F4, and the forms of E6, E7, E8 that have rank 4. But if you don't like exceptional groups, there's also an infinite class of classical groups that have these so-called modular forms. So namely, if you take a group G that's isogenoous to SON4, so at the real place, then these groups will support these modular forms. So if you don't like exceptional groups, everything I'm going to say has, or many things that I'll say have analogs to SON4, and so you can think about that if you don't like exceptional groups. Okay, so all of these groups here, so take the adjoint form and the maximal compact subgroup. K inside the real points. And so for all of these groups, the maximal compact is of the form SU2 times L mod some mu2. So for example, in G2, the maximal compact is SU2 times SU2 mod mu2. And in particular, for all of these groups, the maximal compact always has a normal SU2. So that's sort of an important property that was singled out by Gross and Pollack. So now take so to compare this with the Hermitian symmetric space case, if H is a reductive group that has a Hermitian symmetric space, then the maximal compact always has a normal U1 subgroup. Okay. Okay, so I'm going to, for the interest of time, I'm going to skip this slide. Okay, so Gross and Pollack singled out these representations on the real points of the group G called quaternionic discrete series. And so, these representations have a few properties. So one of them is that they have a very simple minimal K-type. So the maximal compact here is this SU2 times L. So one representation of this is if you take the 2n symmetric power of the SU2 and the trivial representation of this group L. So that's why I'm not telling you what it is. It'll only act through its trivial representation, so it doesn't really matter. So this is a sort of the best you can do in terms of simple minimal K-types of discrete series representations. So this group K has no one-dimensional non-trivial representations. Another important property of these discrete series representations pi n is that Gross and Pollack realized that the restriction of them to this normal SU2 is admissible, so each K-type appears finally many times. And they also have the smallest possible Gelfand-Kirillov dimension among the discrete series of this group G, of the real points of G. So these are sort of analogs of things that are true for the holomorphic discrete series on groups that have Hermitian structure. Okay. So here's this is the classical result here that makes the Fourier expansion of holomorphic modular forms very robust. So this is just some representation theory. So take a group H that has Hermitian structure. The symmetric space has Hermitian tube structure. And then these groups have a maximal parabolic, which I've written as P sub H, the Siegel parabolic. So this is a maximal parabolic with abelian unipotent radical. And so for example, in SP2N, this is the parabolic with Levy GLN, and the unipotent radical is abelian. Okay, so here's a classical result, a classical multiplicity 1 result, which makes the sort of the Fourier expansion of holomorphic modular forms proceed. So if you take a holomorphic discrete series, which I've written as tau k here, and a unitary character of the unipotent radical of this Siegel parabolic, which it could be a degenerate character, it could be the trivial character, then it turns out that the dimension of this Hom space between this holomorphic discrete series representation and this character is always at most 1. Okay? And so even if the character is degenerate or trivial. And so and moreover, if you take a functional L that spans this Hom space, and you take a vector V0 spanning the one-dimensional minimal K-type of this holomorphic discrete series representation tau k, then you can consider this function on the Levy of the Siegel parabolic given by act on this vector spanning the minimal K-type, and then put that into the functional L. And then so that gives you some function on the Levy, and it turns out you can write that function very explicitly. Okay, so that's basically the function, the exponential function that appears in the Fourier expansion of holomorphic modular forms. Okay, so this is the sort of a representation theoretic way of stating what's so robust about the Fourier expansion of holomorphic modular forms. Okay, so the first main result is that this theorem carries over to these quaternionic discrete series in sort of as much as you could hope. Okay, and so if you have one of these groups G that are sort of the main players in this talk, so SON4 or one of these exceptional groups with rank 4, then there's a special parabolic, the Heisenberg parabolic. Could happen to anyone. Okay, so take G to be one of these groups. That's the subject of this talk, and take this Heisenberg parabolic P. And so I've written the levy here as H, and the unipotent radical is N. So the unipotent radical is a two-step unipotent radical, so we'll call the center Z. So then Z is one-dimensional, and then N mod Z is a abelian. And so, for example, in the case of SO n plus 2, 4, this is the parabolic with levy GL2 times SON2. And for example, in the case of E8, this is the parabolic whose levy is this group of type E7 with rank 3. And the 56-dimensional representation of E7. And so in all of these cases, for all these groups, the levy of this Heisenberg parabolic is a group that has Hermitian structure. The symmetric space has Hermitian structure, so that's why I've called the levy H. So you can just look at the examples if you want. So like F4, the levy of this Heisenberg parabolic is GSB6, and so forth. Okay. So here's the first main result. So take a representation pi n on one of these groups that's a quaternionic discrete series, or another very similar representation, and suppose you have a non-trivial character of the unipotent radical of the Heisenberg parabolic. Non-trivial unitary character. So very important, I've bolded the non-trivial because I don't just mean non-degenerate, but it could be a very degenerate character. So that's important. So this Hom space between one of these representations pi n and chi is most one-dimensional, and it's 0 when chi is not positive semi-definite, so that's some condition on characters, which is supposed to be analogous to the positive semi-definiteness and the Fourier expansion of holomorphic modular forms. And moreover, there's take an L spanning this Hom space. It's the most one-dimensional, and from such an L, you can define a function on the levy of this Heisenberg parabolic to the dual of the minimal k-type via the value on an element h and the levy, and then applied to the vector is you take h applied to the vector, and then put it in the functional. So that gives you some function from the levy to the dual of the minimal k-type, and then it turns out that this this function has can be written down completely explicitly and normalized even integrally. Okay, so and then if the character chi is non-degenerate, meaning that its orbit under the levy h is open in the space of characters, then part 1 of this result is due to Nolan-Wallach. Okay. So it's not a technical term, but what I mean is, let me explain just a little bit. So you have a complex line of these functionals L, and then this k-type is, of course, irreducible. So you have a complex line of identifications. Hom k to itself is one-dimensional. So for any such identification in any functional L, you can form this function from h of r to the dual of the minimal k-type. And so you have this complex line of those. And the part 2 is saying that you can write down this function so explicitly that you can just literally write it down without any ambiguity. There's a choice that's so natural that it's completely ambiguous. So unambiguous. So in any way, a later slide will just have what the exact formula is, which is really what I mean. Yeah, I just can't remember it off the top of my head. Yeah. Yeah. Okay. Okay, so a few remarks. So this is just what I was sort of saying before, that the multiplicity 1 result and the fact that these functionals W chi, these functions W chi can be written down so explicitly as to be defined even over Z is sort of what makes the Fourier expansion of modular forms on exceptional groups really go. One statement in this theorem is that chi was non-trivial, so this is the best you can do. If chi is the trivial character, you in fact have infinite multiplicity. But the description, you can still completely describe this Hom space. And then finally, I wanted to remark that the dimension of this uniform radical is relatively small, so the multiplicity 1 statement is sort of surprising even for non-degenerate chi, the case due to Pollack, but it's even sort of more surprising for the degenerate characters. So it's a very special property of these particular representations and this particular parabolic. Okay. Okay, so how does one prove this? So what you do is, we'll take the Cartan decomposition of the Lie algebra of the group G, and take any functional on the representation that's equivariant for this character. So namely, L of n times V is chi of n times L of V for anything in the uniform radical n of R and any V in the space of this pi n. And so for such an L, you can define this function, W sub chi of L from the levy to the dual of the minimal K type, just as in the statement of the theorem. And the Lie algebra action of the P, so the -1 part of the space of the Cartan decomposition, so it gives rise to a huge system of linear differential equations satisfied by this function W chi of L. So which I've written as dn of this function W is 0. So dn is that differential operator. So this is doing this is a sort of a standard procedure which goes by the name of the Schmidt equations or the Schmidt operator. And so then you write them down, and then all the work is solving the equations explicitly. So it turns out you can do it. So steps 1, 2, 3, and 4, and 6 are very easy, and step 5 is where all the stuff is happening. And so because you can solve them all explicitly with moderate growth, I mentioned this is an analytic result in the sense that this Hom space is at most one-dimensional for moderate growth functionals. It's like a two-dimensional space algebraically. Okay, so there's a complex line of moderate growth functionals. And then from the fact that you've solved this system of equations explicitly, and it's just one moderate growth solutions, you deduce the uniqueness of the functional. Okay, so the main theorem is really the explicit form of this function W chi, but it's easier to say it representation theoretically first. Okay. I'm going to skip that for now. And so this is what the explicit formula looks like. So I guess let me go back and I'll say what's going on here. So you take the Heisenberg parabolic and in these groups G, and so like I said before, the Levy subgroup H is a similitude group whose symmetric space has Hermitian tube structure. So denote by nu the similitude, and denote by so remember Z was the center of the uniform radical, the Heisenberg parabolic, and W denotes n mod Z, so the abelianization of that uniform radical. So this group W has a symplectic form, and the conjugation action of H on W preserves that symplectic form up to similitude. And then moreover, W also has a quartic form, and H, so a symmetric four-linear form, and H preserves this quartic form up to the square of the similitude. Okay, and so what is the explicit formula? Not that it's not so important, but it's only, the importance is that it's so explicit you can just write it down. And so the unitary characters of this uniform radical n are of the form chi of n is e to the I times the symplectic form evaluated on, say, omega chi symplectic form evaluated on this n. Okay, so you take the image of n in this n mod z, and then you fix some w chi in this abelianization of the uniform radical n, and then so once you fix such a w chi, then these are all the unitary characters, and so here's the explicit formula for this function w sub chi. So namely, you take a particular basis of the minimal k type, which is a sort of a U1 weight basis, and there's some special element which you have to give it some name, in the complex points of this abelianized unipotent radical. And here's the explicit formula. So you evaluate it, W chi of H on this V sub L, and it involves K Bessel functions of L. So L is an integer here between minus n and n. And you've got some similitude factors, and you've got some symplectic forms and some absolute values. So just completely explicit. And I mentioned that the Hom space was at most one-dimensional, and it's zero-dimensional if this character doesn't satisfy some positive definite condition. And the positive definite condition forces this thing that you're putting into the K-Bessel function to never be zero. So this K-Bessel function diverges at 0, and so it would be bad if you were putting 0 into it. Okay. Okay, so this was the representation theory. Sorry. Okay, so using these quaternionic discrete series representations pi n, Gangros and Savin had sort of defined modular forms on these groups G, in particular on G2. And so roughly speaking, the modular forms are the automorphic functions that generate one of these representations pi n under the action of G of R. And precisely, they define the modular forms to be the homomorphisms from pi n to the space of automorphic forms, the GR equivariant homomorphisms, okay, in particular for G equals G2. And using Wallach's non-degenerate multiplicity 1 statement, so the theorem that I mentioned before, Wallach could prove that this Hom space is at most one-dimensional for non-degenerate characters, and so the new parts of this theorem are the degenerate characters and the explicit formula. So using just Wallach's multiplicity 1 for non-degenerate characters, Gangros and Savin had defined the non-degenerate Fourier coefficients of these modular forms and computed a couple examples on G2 for some Eisenstein series using work of Zhang and Rallis and what you could call a theta function or something. Okay. I'm going to skip this slide. Okay, so you can broaden the definition of modular forms just a little bit, which can be helpful. So namely, so what is the definition? So take one of these groups G, and suppose you have an automorphic function. So fix it at positive integer n, and suppose you have an automorphic function from G of the Adels mod GQ to this dual of Vn. So let me just write down. So Vn is always this 2n symmetric power of the two-dimensional representation of SU2 tensor, a one-dimensional representation of some group L, which I've not told you what it is. Okay, so take automorphic functions that map to the dual of this space Vn and satisfy f of g k is k inverse f of g for all g and G of the Adels and K in this maximal compact subgroup of G of R. And then call such a function a modular form of weight n if this function is annihilated by this linear differential operator dn that showed up in the proof of the theorem. Okay, and it's also on this slide, which if you want to look at later, I think the slides are online or something. Okay, so if you were to so you should think of the dn as sort of the analog for these quaternionic discrete series of the Cauchy-Riemann equations for the holomorphic discrete series. So if you were to do the sort of same thing for automorphic functions on groups that have Hermitian structure, you could write down this linear differential operator dn, and you would just out would pop basically the Cauchy-Riemann equations. Okay, so there's sort of an analog of that. Okay. So examples of such modular forms. So for example, if you take the automorphic minimal representation on E8, so Wietek Gahn, of course, had studied this automorphic minimal representation a lot, and so there's a function that generates this automorphic minimal representation that's a modular form of weight 4 on this group E8. Another example that I mentioned before, if you take a holomorphic modular form on the Levy subgroup of the Heisenberg parabolic, so for example, on E8 again, for example, or say, let's say on G2, so then H here is GL2. So if you take a holomorphic modular form on GL2, then you can form an Eisenstein series on G2 from that holomorphic modular form. And if the weight is sufficiently large, then at a very particular point, S equals n plus 1 in the normalization that I'm using, at a very particular point, this Eisenstein series becomes a modular form of weight n in this setup. Okay, so the corollary of the main result that I mentioned before is that there's a nice sort of robust Fourier expansion for these modular forms on exceptional groups. So this is the statement of that. Okay, so suppose you have a modular form of weight n on one of these groups G. So G could be G2. It could be SON4 if you only like classical groups. And now take the center Z of the unipole radical, the Heisenberg parabolic, and take the constant term of such a thing along Z. So it turns out for precisely the groups that I'm discussing in this talk, so all these exceptional groups and all those SON4s for n at least 3, that this constant term is never 0, or precisely if the constant term is 0, then the function was 0. So once you take this constant term, then you could Fourier expand along the abelianized unipole radical. And so this corollary tells you what that Fourier expansion looks like. Okay, so this is just notation. Denote by n the identification of this W, which is just some symplectic vector space with the abelianization of the unipole radical. And then, so the statement is that, so if you have some modular form F, say of weight n, and then for each W in this symplectic vector space, or 2 pi times the rational points of the symplectic vector space, there are complex numbers A of W, so that when you restrict this constant term of F along Z to n of x times an element in this Levy, then you have this Fourier expansion. So the first term is the constant term along the whole unipole radical, and then the other terms are just the non-trivial Fourier coefficients. Okay, and then the constant term is also interesting. So the constant term is basically a holomorphic modular form on the Levy subgroup of the same weight n plus some constant. Okay, and this phi prime here is basically the complex conjugate of phi. Okay. So once you have this corollary, then you can make the following definition, namely, what are the Fourier coefficients of a modular form of weight n on some exceptional group? So namely, the Fourier coefficients are these numbers A of W that appear here, so the things multiplying these this special function that we have an explicit formula for, and the number beta, which appears here, and the Fourier coefficients of this holomorphic modular form. Okay, so which makes sense because it's holomorphic. So if it weren't holomorphic, then it wouldn't be, you couldn't necessarily talk about its Fourier coefficients. Okay, okay, and so here's the consequence of the fact that you can write down such an explicit formula for these W chi's that it's integrally normalized. So this sort of actually answers Yannis's question. So this theorem does. So there's a modular form on G2 of weight 4 for which all the Fourier coefficients are integers. So if you didn't have an integral normalization, you couldn't make that such a statement. And so this is a modular form of weight 4 whose constant term, which is a modular form on GL2, is Ramanujan's delta function. This constant beta is 0, and all the Fourier coefficients AW here are integers. So this automorphic function was constructed by, defined and considered by Gongroves and Savin, who computed or gave an expression for the non-degenerate Fourier coefficients of this F delta. But so that the new thing here is the constant term and the degenerate coefficients. Okay. 15 minutes. at the moment, I have one modular form that has integer Fourier coefficients. Yeah. Oh, here because I mean, I'm gonna a slide later is going to explicitly define this automorphic function, and so it follows from computing it. No. So what's wrong? Or what's? Oh, this says fz equals 0 implies f equals 0. Oh, no. It's just a soft argument. It has nothing to do with these modular forms. It only has to do with the groups. It's true for any automorphic function on these groups. Yeah, it's just. So I have SON4 for n at least 3. It's false on SO24. Yeah. Okay. 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 So anyway, so this theorem might suggest to you that there's not necessarily so much going on in the degenerate Fourier coefficients, but there actually is a lot. So going on in the degenerate Fourier coefficients. So that theorem is actually a corollary of this result, which gives the Fourier expansion of this modular form generating the automorphic minimal representation on E8. So take this minimal representation on E8 and take the function that generates it. So it's a modular form of weight 4. And the theorem computes this Fourier expansion explicitly. And so the AWs are basically sigma 4 of n's, so the sum of the fourth powers of divisors of n. The constant term of this modular form sees Kim's modular form on E7 that generates the minimal representation on E7. And then this beta is actually very interesting. It turns out to be zeta 5 over 2 pi to the fourth. So all the coefficients except for this beta are integers, but the beta is presumably not an integer. So I like to call the modular forms, to write them with a capital F. And so this theta that generates the automorphic minimal representation is sort of a canonical modular form of weight 4. And so I called it this, and then I realized I needed a better name for it. This is the more descriptive name for it. Okay, so I'm going to skip the proof of this because it's on the slide, so you can just read it if you want. Because I want to talk about a few other things. So, okay, so recall that if you have this Heisenberg parabolic P, the levy is this group H, and the uniform radical I'm writing is N, and W is this abelianization. And so you have the conjugation action of H on W. And so over the complex numbers, there are 4 non-zero orbits of H on W, which are people call rank 1, rank 2, rank 3, and rank 4. Unless you're in the case of G2, in which case there's only 3 orbits. And so even though there's only 4 orbits over C, there's infinitely many orbits over the rational numbers. Okay. So I want to tell you about some modular forms that have interesting Fourier expansions from the point of view of arithmetic invariant theory. So that means from the point of view of considering these orbits of H on W over Q instead of over C. Okay. So for example, on G2, this space W is essentially the symmetric cube representation of the two-dimensional representation of GL2, and elements of W are binary cubic forms. And so this is just to give you some sense of what these rank 1, rank 3, and rank 4 guys look like. So take complex numbers alpha, beta, gamma, which are pairwise distinct. So rank 1 things are the most degenerate binary cubic forms. Rank 3, so there's no rank 2 for the case of G2. Rank 3 are things where you have 2 equal roots, and rank 4 are the things where you have 3 distinct roots for these binary cubic forms. Okay, so so like I said, H acts on W, and there's a quartic form, which is preserved by the conjugation action of H up to the square of the similitude. And the rank 4 things here are precisely where that quartic form is non-zero. Those are the non-degenerate orbits. Okay. And so if you take all the rank 4 things and apply the quartic form, you get a map into Q cross mod Q cross squared. And so you can think of that as the quadratic Étale extensions of Q. And so a fact is the following. So if you take a modular form on these groups G and take such a W for which this quartic form is positive, so in other words corresponds to a real quadratic extension of Q, then the Fourier coefficients associated to such a W are 0. So this is just a consequence of that positive definiteness thing that I mentioned before. So the Fourier coefficients are always 0 for things that are not positive definite, and these W's are not positive definite. So in other words, you can only have rank 4 coefficients corresponding to imaginary quadratic fields. So fix an imaginary quadratic field extension of Q, call it E, and associated to E, you can define a group of type E6 over Q, so that's a group I'm calling GE. And so here's the result. So there's a non-zero weight 4 modular form on this group of type E6 defined in terms of E, such that if you take a W that's rank 4 and a quartic form on it gives you a class that does not represent E, then the Fourier coefficient associated to that is 0. And on the other hand, there is a W that represents this imaginary quadratic extension such that the Fourier coefficient is not 0. Okay, so classically, in the case of holomorphic modular forms, these sorts of things are called distinguished, which means that you have sort of one orbit of non-zero, non-degenerate Fourier coefficients, and all these other non-degenerate Fourier coefficients are 0. So this modular form sort of sees the arithmetic of the orbits of H on W in that there's one sort of distinguished orbit where you have non-zero Fourier coefficients and the rest are all 0. Okay. So how do you prove this theorem? So you define this group GE, which I said is simply connected, or it's of type E6. It's a group over Q, which is over the real numbers, is of type, has rank 4, okay, and it's of type E6. And then you very carefully embed this group inside of E8 via some embedding iota sub E. And then you take this modular form generating the automorphic minimal representation on E8, and you pull it back to this group of type E6 via this embedding. And because you've defined this guy in terms of just pulling it back from E8, you can compute the Fourier coefficients of this function theta E. And so the guy on E8 that generates the automorphic minimal representation, it only has non-zero Fourier coefficients for the very degenerate W, precisely because it generates the minimal representation. Okay, so precisely it only has non-zero Fourier coefficients for those W of rank 1. And so the fact that this guy on E8 has only non-zero Fourier coefficients for W of rank 1 imposes a really strong sort of arithmetic condition on the Fourier coefficients of the pullback to E6. Okay, and so that's how you get that all of these, most of these Fourier coefficients are 0. Okay, so that's how you construct a distinguished modular form. And then you can also construct a singular modular form, which means that the non-degenerate Fourier coefficients are 0. Okay, so via the same process. So this time fix a quaternion algebra B over Q that's ramified at infinity. And out of that quaternion algebra, you can construct a reductive group G sub B, defined in terms of B, which is simply connected semi-simple of type E7. And again, you can carefully embed this group into E8 and pull back this guy generating the automorphic minimal representation to E7. And what you get is a non-zero weight 4 modular form on this group of type E7. And the rank 3 and rank 4 coefficients of this function theta B are 0. So remember, the orbits of H on W of this levy on the abelionized unipotent radical. There's 4 non-zero orbits over the complex numbers, rank 1, rank 2, rank 3, and rank 4. So here the rank 3 and rank 4 coefficients are 0, and there's a non-zero rank 2 Fourier coefficient. Okay. So finally, I want to mention something about L functions. Okay, so on G2, so the Fourier coefficients are parameterized by binary cubic forms, which you can also think of as giving you a tall cubic extensions of Q. And it's a fact, an easy fact, that if you have a level 1 even weight modular form on G2, then the Fourier coefficients are 0 unless this W is integral. And moreover, that they're equal if you translate W by the action of GL2Z. So in other words, the Fourier coefficients correspond to orbits of GL2Z on a lattice inside the binary cubic forms over Q. Okay, and those orbits correspond to cubic rings T, so commutative rings T that are Z cubed as a Z module. And so if you fix a cubic ring T, then you can define the Fourier coefficient of a modular form on G2 that corresponds to T via the Fourier coefficient of that modular form for W, where W is any sort of binary cubic that corresponds to T. Okay, and the positive definite condition written this way for cubic algebras is that the cubic algebra has to be totally real. So it's the Fourier coefficient is 0 unless T tensor R is R cross R cross R. Okay, so this was a setup for the last slide here, which is what L functions look like on G2. So suppose you have an automorphic cuspidal representation on G2 that's level 1 weight K modular form. So I'm assuming that it's unramified at every finite place, but that's just for the purpose of writing the slide. It's not important for proving the results. It's not. So fix a totally real extension, totally real cubic Attal extension E of Q, and denote by O sub E the maximal order in E. So if you have an even, if K is even, so an even weight modular form, and then take the primes S that consists of 2, 3, and all the primes that ramify in E, then you can, on the left-hand side here, you can form this Dirichlet series in terms of the Fourier coefficients of this modular form. So what's written here is Z plus N times T. So T is a cubic order inside this OE, and you multiply by N, and then Z plus NT is still a cubic ring, and so it makes sense to take the Fourier coefficient associated to that cubic ring, and then you sum this over the cubic orders sitting inside E, OE, and N at least 1 that are both prime to S, so meaning this index is prime to S and N is prime to S, and what you get is the partial L function for the standard representation of this cuspidal guy pi. Okay, and so this is just a small improvement on a work of Nadia Gravich and Agner Segal. So they gave a Rankin-Selberg integral that is non-vanishing for modular forms on G2, and the improvement of this is just eliminated some bad places in the results. Okay, so I'll stop there. Oh, I mean, so most of the talk is just about representation theories. It was only this last slide where I've really used anything about where the representations are unramified at the finite places. Sorry, what's that? Yeah. So the whole theory takes place at the Archimedean place. So you're interested in the automorphic representations that have, at the Archimedean place, a very particular representation sitting there, and then, what's that? No. It just, yeah. All that does is change. So that's, maybe, let me put it this way. was trying to pull here. So in the Fourier expansion here, I wrote W in 2 pi times W of Q. And so if you were unramified at every finite place, then all the Fourier coefficients are 0 unless this W is in 2 pi times W of Z. And then if you have more ramification at the finite places, then that lattice where the Fourier coefficients are supported just becomes bigger inside of this. Not yet, no. Oh, that's right. Yeah. This result is for yes, for cuspidal representations. Yeah. Well, so there's a discrete series at infinity, so you know that there will be lots of cusp forms, but no one has constructed a specific example of them. Yeah. Mm-hmm. Uh-huh. Yeah. That's a great question. So the huge obstacle is that all the symmetric spaces, they don't have complex structure, so there's no algebraic geometry in sight. So it's a huge obstacle. So it would be fantastic if one could prove some sort of algebraicity result, but I don't know even what one would precisely conjecture. Yeah.